everybody. Sorry about that. I was answering email really quickly. I need to hit a button real quick here. There we go. Welcome back to Chem 161. We are going to start Chapter 5 today. Chapter 5 is short, and we're not going to do all of it. It's possible that I might actually finish it today, but I'm going to try and take it slowly. Because the stuff that's covered in this chapter is a little bit weird. But it is super, super useful for you if you are a biologist or a chemical engineer or chemist who's going on to organic chemistry. So it's sort of unfortunate that this section is so divorced from when you will actually encounter these ideas in OChem. Yeah, that's kind of where I guess that's what I'm going to lead off with is I wish that we did this later. All right, so let's talk about valence bond theory, which we're going to learn is a bunch of bullshit. It's a good starting point, but it's just not that great. So how do we make a covalent bond? So we have talked about how if I want to form a covalent bond, that I need to do something like, say, here's my carbon, and then here's a hydrogen. And what I would do is I would have these two electrons share. And I would form the bond. That looks great on paper, but what does that realistically mean physically? And so the answer to this is, well, if my carbon atom has orbitals, and those orbitals are things like this, so there's my carbon, and here's my hydrogen. If I have my electrons like this, and I want to share them, what I'm going to do is I'm going to just put this in a spot where the two orbitals are in the same physical location. In other words, my 1s orbital on hydrogen would overlap with one of these other orbitals that has an empty space in it for an electron to be paired. So that'd be one of these two p orbitals, although later on we're going to learn that this is not quite right, which is why valence bond theory sucks. But the intent is that I can just move two orbitals and overlap them, and the bonding will occur in the overlapping region. So here I got a bunch of s orbitals on the left, and here I've got a variety of orbitals on the right. What I'm going to do is I'm going to push them along this y-axis such that the two orbitals bonk into each other. And if they can overlap, then I can form a bond between those two orbitals. But if they don't overlap for some reason, maybe like spatial geometry doesn't work out for them to overlap, then we'll know. Oh, yeah, thank you. I am feeling a lot better today. So, regarding Thursday, we'll just pause for a second real quick. So, regarding Thursday, I had to cancel the lecture, so I hope that everybody was able to read the rest of, or watch the rest of Chapter 4, or at least will in a little bit. I realized there were 2 lectures worth. I just really wanted to make sure that we got Chapter 5 done. And now that I'm looking at how much Chapter 5 there is, I'm like, oh, maybe I overestimated how much time I needed. But I went to the doctor. I made an appointment online, went and picked up a prescription for antibiotics. I instantly felt better, the next day. I went from crazy sinus pressure and, trauma and green crap coming out of my nose everywhere to, oh, everything's gone. And so, I'm, 95% of the way better. The cough is still kind of there, but I'm not, so congested that I can't breathe. So, all right, so what we're going to do is we're going to combine these orbitals together. So I'm going to take this s orbital, I'm going to combine it with this s orbital, and we should see that these should be very able to overlap if I move them along this y-axis, and they totally do. All right, but what about this next combination? You'll see that my p orbital is arranged along the x-axis, and so what the s orbital on the left is going to do is when it gets over there, it's going to sort of nose on in there, and yeah, and that doesn't work, right? So, like, it's nestled between the nodes. It doesn't actually overlap them, though. Same thing sort of happens here, is when we let these two go over here. Yeah, it just doesn't, there's no overlap. But this one, the p orbital is oriented along the axis that the orbital is moving, so these two will overlap just fine. There's my game show sound effects for you to show how these orientations matter. So if you've ever wondered, why do we have p, x, p, y, and pz? And it's for this reason. In space, there are 3 dimensions, and those 3 dimensions matter when it comes to whether orbitals will physically overlap with each other or not. So only some combinations will lead to bonding. I've shown some examples here of s orbitals where I could put my electrons like this, because initially here's an s orbital and here's an s orbital, and this would look like this. When I overlap them, the 2 electrons pair together in the overlapping region. And so here would be that for this s and this p orbital. Here would be that for this p orbital and this p orbital. What do the different colors mean? Those are the phases for the orbital that is the result of the Schrödinger equation. Remember that orbitals are represented by an equation that we didn't go over because this is an introductory class. And that equation can have positive solutions or negative solutions. The blue regions are considered to be, we'll just call them positive solutions, and the red ones can be negative. All that really matters is that when you overlap your orbitals, you overlap them with the same phase. Because overlapping orbitals is like adding them together. If I overlap 2 blues, it stays blue. But if I overlap a blue and a red, they cancel and I get nothing. And electrons don't want to sit in nothing, because that's not where the overlap occurs, right? If we get to MO theory, I'll talk a little bit about that later. Linear combination of atomic orbitals. Now, these are all the combinations where I line things up along an axis. And you can see the little dots in the middle. Those dots represent nuclei of atoms. Now, there's actually another arrangement where I could get overlap, and that overlap looks like this. If I take 2p orbitals, and I make them perpendicular to the axis that I have my nuclei running along, and those 2p orbitals are both parallel to each other, then interestingly, they overlap in the middle. Right here. That orbital is very obviously different than the other ones, right? There's something weird going on about that one. However, it is still an overlap, and it does count. We're going to define types of bonds in the following manner. If I draw a line through my nuclei, so like this. In fact, I'm just going to draw the same line all the way across. If I draw a line through my nuclei, and that line passes through where my electrons would be in the overlapping region, the bond I have is called a sigma bond. Sigma bonds require electron density to be on this line. This line that I've drawn is called the internuclear axis. I swear, I try to save my handwriting on this on PowerPoint far more often than I really should have to. Now I'm looking at it and it looks like internude ear. So I'm just going to fix this. Internuclear. There we go. So again, if our electrons are on the internuclear axis, or in other words, the region in which the orbitals overlap is along this axis, the bond is a sigma bond. Over here, where my electrons pair, is not along this line. It's above and below the line, right? So we're going to call that something different. That's going to be called a pi bond. In a pi bond, the electron density is parallel to the internuclear axis, but does not run through it. A pi bond is kind of weird. It is not a linear bond. It's sort of this strange sort of bent bond, except that it's also down here too. Because my electrons are occupying both of those spaces at once. What? Electrons are weird. We've talked about that in quantum mechanics, right? Electrons are strange. Remember that electrons are a wave function, and because they're behaving like waves, they basically exist in the orbital. They are everywhere at once, which means they occupy both of those sides. The only space that they don't occupy is in the node, which is right here. So the electrons cannot be between the nuclei and also be in a overlapping p orbital. If we're in a pi bond, I should say. Whenever you form a bond between two atoms, the first bond is always sigma. So if this is my nucleus, and this is my other nucleus, and I form a bond, my bond must form from the overlap of orbitals between the nuclei to make my sigma bond. That's because this is the best attraction that could be formed. Nucleus, which is positive, electrons, which are negative, nucleus, which is positive, all in a line, perfectly normal, I guess we'll call it. It makes sense, though, that charges should propagate in lines, right? However, there's an issue, and the issue is once I form that first bond, I cannot put any extra electrons in that space. It's already taken. So the next bonds have to go parallel to the internuclear axis, and they would be something like this. So if I had a p orbital like that, and a p orbital like that, then the overlap would be in this region right here, if I could make the p orbitals wide enough, but I'm drawing my diagram really poorly. So the electrons would be in this overlapped region, and there's also an overlap down here. And then if I wanted to do another p orbital, well, I've got the other orientation because I've got three axes, right? This one would go in the back here. And come out in the front. This would be in the back here. And it would come out in the front. And then that overlap would go like that, and then in the back too. So I can make a sigma bond and up to 2 pi bonds. And I realize this diagram that I've drawn looks terrible. So what I'm going to do is I'm going to go like this, and I'm going to find the picture that represents what I wanted to draw. There it is. We're going to come to this later. So we can make up to 3 bonds between two atoms. The first one has to be sigma, which is right in the middle here, and that's a terrible color. You can just ignore what's on the screen here. We'll just get rid of it. The first one is sigma. Let's do yellow. That's such a weird color to want to draw in, but it's exactly what I want here. So there's my sigma, and then my pi bonds are this top-bottom pair, and then my front-back pair, which I'll highlight by doing a different style. And of course, my tablet freaks out. So, all right. So we'll come back to that. So there's our summary for bonding. If you make a single bond, it's always going to be a sigma bond. A double bond, the first bond is always sigma. Any further bonds are pi. A triple bond requires a sigma bond and 2 pi bonds. Now, if I draw the structure of something, you should be able to count the number of sigma bonds and pi bonds in it relatively easy. Because remember, the first bond between any two atoms is a sigma bond. So what we're going to do is we're going to take out blue, and I'm going to go like this. 1, 2, 3, 4. Whenever I'm given this type of question, this is what I do. I draw over the bonds, and I say, okay, how many did I overdraw? 7. So there we go. There are 7 sigma bonds. Because the first bond is always sigma. And then I would go and pick some other color, and then I'd fill in the remaining bonds. So I'd go 1, 2. And that must be how many sigma and pi bonds there are. You do this with any Lewis structure that you can draw. All right. We've seen this diagram before. We talked about how bonds form when orbitals overlap in chapter 4, just a little bit. Now, we also said that if you have your orbitals completely overlap, then what happens is that the nuclei bonk into each other, and that's bad. 2 nuclei have the same charge, so they're not going to want to occupy the same space. If they do, a repulsion forms, and the amount of energy that is required for us to keep those molecules in that location grows very, very quickly. So they would repel almost instantly. There's got to be some optimal distance where the bond that forms between the electrons in the overlap and the 2 nuclei of the atoms surrounding it has the optimum potential energy. In other words, there is the ideal attraction. It is the best distance that the two entities can be from each other. For every bond, there is a particular length associated with that. That length will be measured in some unit, and there is a potential energy that is required to tug those two things apart. If I had a mole of hydrogen, which is what this is, I would need 436 kilojoules to completely break apart all of the molecules in that sample. So this is how you end up with specific bond lengths. Now, typically speaking, the shorter a bond is, the stronger it is in energy. But this is going to require or rely upon several features. For instance, one of those would be things like electron affinity. How strongly are electrons attracted to the nucleus of an atom in the bond? Sorry, when I said electron affinity, what I meant was electronegativity, which is electron affinity and other features summed together. Now, the difference in electronegativity also matters. So if I have two atoms that have very similar electronegativities, then those atoms are going to buddy-buddy real good. So a carbon-carbon bond, very strong. Carbon-hydrogen bonds are quite strong. Other bonds depend. Now, the general idea behind these principles leads us to this idea called valence bond theory, which is if I take my valence electrons, I can create bonds with them using whatever orbitals they are sitting in. So what we're going to do is we're going to take unpaired electrons in our valence orbitals. Wow, that was the worst line I could have drawn. We're going to take unpaired electrons in our valence orbitals and pair them with other unpaired electrons on other molecules. And so that's going to look something, well, okay, and then if we have paired electrons, they just sit there, they hang out. They become the dots that we draw in our Lewis structure. That's going to look something like this. And you're going to look at this model and be like, wow, this is so elegant. This must be absolutely right, and it's totally not. So for example, let's draw the Lewis structure for H2S. Here's my H2S molecule. Now let's show how the orbitals align themselves. Well, if I want to bond sulfur to hydrogen, I need to pair up these two single electrons on each atom. So I could pair the H with one of the unpaired electrons on my S. I could pair the other H with the other unpaired electron on my sulfur. And then these would just be my non-bonding pairs of electrons. And so when I get this, that's these guys right here. And, like, it's so elegant. Like, holy crap, everything matches up. Everything that we've learned comes together with this nice, neat bow. This has to be the solution. And that's what people thought. And then they were like, oh, fuck, when they got to this. Oh, hold on. I forgot. I have a sound effect here, don't I? Yeah, this is the surprise, totally wrong. I already spoiled that, but... So this is a great idea in principle, but there's a serious fault in it. And that arises when we get to carbon. How the heck do I deal with carbon? Carbon has something that looks like this. And all along for its Lewis structure, we've been drawing this, right? Furthermore, in the geometry section, which we were going to do on Thursday, but then I could not continue because all I was doing is coughing and sneezing. Hopefully you have watched the video for Thursday that talks about geometry. The geometry of something with 4 entities coming out of it is tetrahedral. That doesn't work when all you have are XYZ coordinate axes. How the heck do I get something tetrahedral? Also, how do I reconcile this? This doesn't even match. Where's the lone pair on carbon? There's not one. It's not that we've been doing the Lewis structure wrong. It's that valence bond theory is broken. It doesn't work. And the reason it doesn't work is because there's something wrong with what we know about it. So all of these things don't match up. I cannot get carbon's electron configuration to look like what we draw for carbon when we're bonding, nor can I get carbon, which often forms tetrahedral compounds, to align to this idea that we have up here. And we know that it's not that our model is wrong, because CH4 exists. CH4 is methane. That's natural gas. This is one of the most common compounds in the universe. I'm not going to question that. We're going to question our model. It's us. It's our fault here. It's not nature. But why? And so we ditch valence bond theory and we go to this new theory, which is called hybridization. Hybridization is a model. Hybridization is our intent to understand what's going on. We're basically making shit up. So when you say, "How do you blend orbitals, Professor West?" and I'm gonna be like, "You don't actually blend them." But what we are going to do is we are going to take our s orbital and our p orbital. We're going to throw them in the blender and turn it on puree. And then we're going to pour whatever is left out, and that's going to make hybrid orbitals. At this level of chemistry, that's really just the best explanation that I can do. In reality, what we're doing is we're taking the weighted average of all the Schrodinger formulas for all the orbitals, and then averaging them out, and then the end result we get has a different spatial orientation. Because you can add functions together, right? Like if I say x plus 3 and x plus 4, add these together, and then plot the graph, you get a new graph, right? Same thing with three-dimensional graphs, except it's just a lot more complicated. So let's try and show visually what's happening. So we need to make our model support CH4 and not CH2. So we need to do something with this diagram. Here's what we're going to propose. If there was a way to get this box right here to just be right here, then Hund's rule would say, okay, well now I have 4 electrons in 4 orbitals. I'm going to unpair these due to electron-electron repulsion, and then we'll do that. And then that would at least match what we expect for carbon, right? So if I could just get this box for 2s to be the same energy as 2p, I could then unpair my electrons, have 4 unpaired electrons total, and thus everything would be lining up with our expectations of how bonds form with compounds in nature. So CH4 would make sense. So the process that we have our orbitals undergo is called hybridization. When you hybridize orbitals, you select some orbitals and blend them together. I'm going to blend all these orbitals. And this is what I get. You can go back and listen to that sound whenever you want to now, just in case you wanted to. I wouldn't recommend it, but you do you. Now, what is this term that we've written over here? We wrote sp3. We wrote this because I had an s and p orbitals in there. So this is just basically what orbitals were hybridized. So I put an s orbital in and I put 3 different p orbitals in. We're going to call that sp3. Now, because they're all hybridized and they're all blended, they're all the same. So we are basically removing the distinction in energy between S and P. And saying, I want to mix all these together, they are sp3. Now, does this happen all the time? No, it does not. You literally just did a lab on PES that did not detect hybridized orbitals, right? When you looked at your unknowns and had to fill in like all the little questionnaire about like what is the unknown, I think one of them is actually carbon, and you can see the two s orbitals and the two p orbitals. So that shows that the model on the left is accurate to where the electrons are for regular old carbon by itself. So this over here is regular carbon. This over here would be carbon when bonding to stuff. So you can think of this as a sort of mechanism that occurs in order for bonding to take place. Think of it as the bonding activation energy. I invest a little energy to get my carbon to have 4 unpaired electrons available. Then I can make 4 bonds to it instead of 2. All I have to do is pay this little tiny bit of energy first. And if I do that, everyone can now bond. Remember that bonds form between nuclei and energy is released. So we get more energy out by forming these bonds than we put in to hybridize a single carbon. So naturally, this will happen all the time, and it totally does. This idea that we can just take an orbital and then move it to whatever energy we want to, sort of fictitious because we're making up a model for it to work, but it describes what we're seeing pretty effectively. Now, let's suppose that I didn't want to make sp3 orbitals. Could I make like sp2 or something? You totally could. If you hybridize fewer orbitals, you would call it just whatever you put in there. For example, maybe if I only put in an s and a p, I'd get sp. Maybe I want to put in an s and only 2 p's, then I get sp2. We're going to show examples of why you would do sp2 versus sp versus sp3 later on. But for now, all you need to know is how to name the orbitals based on what we are putting in them. We're going to later hook a hybridization to a geometry. So for example, sp3 is always tetrahedral. And that's going to be helpful later on. Now, only molecules contain hybridized orbitals. We hybridize our orbitals in order to make bonds with stuff. Any atoms that are independent or original, not original, any atoms that are independent can retain their initial electronic structure. So, again, with carbon by itself over here, we would observe s and p orbitals, and we would see the peaks for them. But carbon in any compound, carbon in any compound will hybridize so that we can make the maximum number of bonds. I'm going to make everybody yawn, sorry. All right. Now, if I put 4 orbitals in, so 1, 2, 3, 4, I get 4 orbitals out. Those 4 orbitals will contain electrons, and electrons repel, don't they? So they are going to orient themselves as far as possible in 3 dimensions. And that orientation leads to the tetrahedral arrangement with the bond angle 109.5 between orbitals. So let's write that down. We're going to come back and remember this later. sp3 gives us a tetrahedral arrangement of our orbitals around the nucleus of an atom. Cool. We can work with that. Now, if I take my CH4, here's what my CH4 is going to look like before hybridization. Or not before hybridization, but before bonding occurs. I'm trying to draw this the best that I can, but I'm not really an artist, so... There would be my carbon with its 4 unpaired electrons. And then what I am doing is I'm taking hydrogen, and hydrogen has an electron that it's bringing with it, and we're going to overlap our orbitals like that. And that's how we get the structure shown in the middle of the screen there. Now, because each of these bonds goes through the internuclear axis, so if I draw an axis that connects the nuclei, so I'm drawing straight through the letters because the letters are the nuclei, you'll notice that my electrons are always along the internuclear axis. Therefore, there must be 4 sigma bonds. And there totally are. All right, so hopefully this is starting to come together a little bit. All right. Let's take our break now because my cat is howling at me and I need to address whatever she's doing. So I'm going to put the break card on the screen here. Oops, my timer didn't pop up. There it is. I'm going to get more Zelda Wave going. Everybody loves Zelda Wave. This is probably like one of my favorite tracks to stream for you guys. And it always gets dinged for Zora's Domain, which is coming up in 3 songs. So these next 3 songs are really something. So hope you enjoy them. wind that down here. I played a lot of Ocarina of Time when I was a kid. And we come back on Thursday, we'll play Zelda Wave 2, which is Majora's Mask, and I played a lot of that too. So, these are some of my favorite tracks, which is why I'm saving them till the end. Also because I forgot to play them earlier in the quarter, so I was like, crap, what do I play this week? Oh, sweet, I haven't done Zelda Wave yet. Alright, so we did CH4. I want to do NH3 now. So the first thing that I'm going to do is I'm going to put this on the screen here. And I want you to try and figure out, when we hybridize it, what will my orbitals look like? And how will that match up with its structure? So I'm going to give you a few seconds to think about this. I mean, my text on the screen sort of spoils this, but draw the structure, and then try and draw out your structure with the balloons attached to it. And I'll do that in just a second here. But I'm going to give you like 3 or 4 minutes to try this on your own. 1 or 2 more minutes, we'll go over the answer. All right, so my slide is going to put the orbitals on the screen here real quick. So this is just going to, oops, my cursor isn't drawing. This is just going to go up here, right? And then everything will be the average energy. Boop, there we go. You'll notice that if you line these up, I'm not actually moving this up here. I'm getting the average energy, which would be, this should go right through the middle here. It's lower than 2p, but it's much higher than 2s. So my, oh, I'm just going to move this box up here, is not intending to say I move it up here and it's this much energy. I'm moving it so it's level with these guys. But they all come down slightly. So I'm still going to hybridize 4 orbitals. And then what's our diagram, or not diagram, what's our molecule going to actually look like? So let's go over here. That's not Photoshop. There we go. And so I'll put my nitrogen in the middle here. And I'm going to have 4 orbitals coming out of it. So I'm going to have one going like that. One going like this. One will go dot, 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 dot. Like that. And then another one over here. And that one wasn't very good. Let me try that again. That's a little better. Okay. And each of those has electrons in it. So one of them's going to have one. Okay, well, 3 of them will have 1 electron in here. And then the other one will have 2. So there's my non-bonding pairs right there. And then what I'm going to do is I'm going to do this. Well, I'm going to do this, actually. So I'm going to take my hydrogen, and I'm going to put an electron in it. I realize I've made this way too big. Hold on. So we'll put an electron in here, and I'll just make a little hydrogen here. And then I'm going to... We're going to see if this works. This is sort of an idea that I have here, so we'll just go copy-paste. I'm going to... Oops, I didn't mean to do that. So I'm going to take my hydrogen, so I'm going to just pair these electrons. I realize that these are going to be paired in the wrong orientation, but I can fix that in a second. So we'll do that. I'm going to put another one in here. We'll put him here. And then I'll take this last one, which I have to actually select. And we're going to put him... rotate. There we go. Whee! We're going to do that. And then all I have to do is just go like this. Where is the button? There it is. I want this color. And we'll just go whoop, whoop, whoop. There we go. We fixed it. Hooray. That looks it was going to look a lot better in my head, I guess. I don't know. But that's what a molecule of ammonia looks like. Where the top orbital of the sp3 arrangement is where the non-bonding electrons go. So nothing bonds with it. But the other ones have lone electrons, so I pair them with the hydrogens and I get my NH3. Now, how many electron groups are there? Well, there's 1, 2, 3, 4 electron groups. Just to review the geometry that we didn't get to do on Thursday. So again, hopefully you've seen that video. There are 4 electron groups, so the molecular, I'm sorry, the electron geometry of this would be tetrahedral. And of those 4, one of them is a pair of non-bonding pair of electrons, which means that its molecular shape is trigonal pyramidal. And so you can see how this model is actually lining up with our understanding of geometry really nicely. All right, let's do some more shapes here. So let's go back over here. I just noticed something. Hold on. Sorry, I'm just playing with things now and seeing if this changes my settings. I guess not. Okay, maybe they're all linked together. That's good, actually. I don't want my volume to suddenly change when I move from one thing to another. All right, so let's talk about how we make a double bond. So we said that we need to have unhybridized p, well, I shouldn't say that word yet. We need to have p orbitals for pi bonds, right? So those pi orbital or pi bonds look like this. Here they are. But these are p orbitals. These are not hybridized. They're not sp3, sp2, sp whatever. I need to literally have p orbitals. So what that means is that, where am I? I am here. Oh, I'm here. Okay. What that means is that I need to have p orbitals left over. I cannot hybridize them. I need unhybridized p orbitals. If I hybridize a p orbital, it's no longer the correct shape and it's no longer perpendicular to the internuclear axis. It would be at some other angle that doesn't help us. So, when we hybridize, I'm just going to exclude however many p orbitals I need to make a pi bond. If I need to make 1 pi bond, I'll save 1 p orbital. If I need to make 2 pi bonds, I'll save 2 p orbitals. So that's going to look like this. Here's my carbon in C2H4. I'm going to choose one of the carbons, but the other carbon does the same thing as this. So I'm going to save this 2p orbital. It's got an electron in it because I need to pair that with the other p orbital on the other carbon. So I'm going to hybridize the rest of the stuff. So if I throw all of this into the hybridization blender... I lost my pen there. There it is. What do I make? Well, I make sp2. Because I only put 2 separate p orbitals in there as opposed to 3. So now I have sp2 orbitals and the leftover 2p orbital, which I've dyed yellow. What's the arrangement of 3 orbitals in space around each other that's ideal? Well, we saw that in chapter 4. That's trigonal planar, right? So if this is my plane of my paper, my 3 orbitals would be on the plane of that paper. And then the p orbital, so we'll just say that these guys are those. My p orbital goes in the only logical spot that it can really go, which is, well, it can't go in the xy plane, it'll intercept other orbitals. Instead, it goes above and below, hope you can see that part, dot, 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 the plane. So whichever plane I choose for my sp2 orbitals to go on, I will then have my p orbital be perpendicular or orthogonal to that plane. Now, if I have a second carbon that I've done that to, then this is what's going to happen. And so I'm going to draw the structure. We'll save my structure because that's actually pretty good, I think. So let's oops, hold on. Merge visible. Boop. Oh, that's not what I wanted, actually. Undo. Not merge visible, merge layers selected. There we go. Because if I merge visible, I lose the whiteboard part itself. We don't want this. You don't want me drawing on transparent. That looks really obnoxious. So let's draw our carbon atom here. So here's our carbon, and I've got an orbital going like this, an orbital going in. Well, actually, let's do the front orbital first, like that, and then orbital going like that. So these are all in the plane of, we'll just say this. And I don't like this line very much. That's a little better. Okay. I'm going to put my p orbital above and below this plane. Now what I'm going to also do is I'm going to draw a second copy of this over here. So I'm going to put a carbon here. I've got 1, 2, 3. And then we'll draw its p orbital above and below. Oops, hold on. And below that plane as well. And then, we'll do this. So it kind of looks like a dotted line there too. Because this p orbital, this purple lobe, oh, you know what we could do? We could do this too. There you go. Now it looks kind of 3D, right? Okay. So we've got an overlap here. And then we've got 1, 2. Well, let's put all our electrons in here. So for the carbon on the left, that would look like this. For the carbon on the right, I'd go 1, 2, 3, 4. In fact, what I can do is we'll just erase these electrons. Let's just do these in a different color. So you know which electrons belong to which carbon. That's a little more clear. So there's the left carbon. And we'll make the right carbons this blue color. In fact, we'll just point them all down. There we go. So there's the 4 electrons from each carbon. And then what I can do is first of all, I need to get a color here. There we go. I can pair these together. So those orbitals now overlap. We represent overlapping by either drawing them as overlapped, or we do this like line thing, because generally speaking, if you get the p orbitals overlapped, you have to either make them real wide, or you have to draw everything really close together. And it's very hard to then show the s orbital in the middle there. Or not the s orbital, but the The sp2 orbital in the middle there. All right, so we've got overlap there. So there's our pi bond. This is our sigma bond. And then we've got 4 bonds coming out the sides here for hydrogen. So we'll just go... not black. We've already done black. So we'll go hydrogen. I literally said not black. What is wrong with you? There we go. We'll go hydrogen, 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 hydrogen. And there you go. And we'll label these bonds. And there you go. Everything is labeled. The last thing that you can do is you can label your bonds based on what orbitals were used. So for instance, right here, for each of these sigma bonds, we used a sigma 1s and then carbon sp2 orbital. And so that's true for all of these. So I'm not going to write that. But over here, for pi, we used carbon 2p and carbon 2p because those were unhybridized. And then for the sigma, we used carbon sp2, carbon sp2. So when I used to do this class in person, I would ask you to draw these balloon diagrams to the best of your ability and then label all the orbitals as sigma or pi, and then indicate which orbitals were being overlapped so that I would know, because sometimes it was unclear with your drawing. And so labeling it was helpful. Obviously, on Canvas, there's no way for you to make a drawing of these orbitals, but if you are able to do so, I would recommend it, because if you can draw out these diagrams and show this sort of thing, then it helps you understand where in space the electrons are. And true story, I was the one person in my class as a graduate student that passed my master's exam because I knew this shit, believe it or not. My question was, I was working with this molecule, C2H4, and the instructor asked me, where are the electrons in C2H4 if you're holding an eraser, and the eraser is your C2H4 molecule. So I was standing there at the whiteboard, and here's my eraser. And he says, this is your molecule. Where are your electrons? And I pointed right here and right here, above and below the eraser. I was like, well, they're right here and here. And he looks at all the other instructors in the room and then looks at me and goes, yeah, that's right. I'm surprised you knew that. I'm like, that's a first year question. And he's like, yeah, all of these are first year questions, it turns out. They were asking me first year questions as a master's candidate. And everybody gets screwed up on them because, like, this stuff doesn't seem important to you. But in the chemistry I was studying, where the electrons are was very important because this is where your bonds come from in organometallic chemistry. Yeah, you make bonds directly to the pi electrons. It's very strange. But because I knew where they were, because I know basic Chem 161, they were very impressed by that. And apparently nobody else knew the answer to that question. So if you get this right on the exam, you could qualify for a PhD or a master's degree like I did. I was the only one that got a perfect score. Not perfect, but I mean, like, there were 3 grades. There was pass, pass with conditions, and then fail. I was the only pass out of like 25 people, which is insane when I think about it. But yeah, and it was because of this question, I'm convinced. They were all so impressed that I knew that. So now you know it. And all you have to do is be able to draw this diagram, which in reality it looks kind of sketchy, but it's actually not that difficult. I'm going to compare the diagram that the book draws. There it is right there. And let's see if your diagram, or the diagram that I drew, matches up with theirs. When I say the book, this is a different book that I was teaching from, so I copied and pilfered their picture. I don't know. I think it looks pretty similar. I didn't even intend for the hydrogens to be red, so like that was serendipitous. But so hopefully you can see the point here of how we're drawing our orbitals around in our structure and then showing the overlap. They're going to put the electrons right here in the middle, and that's fine. What's important is that we represent that they are paired together, and I think I did that. Yeah, I drew lines between them, so. All right. So that's how we get a double bond. So the double bond is this one. Here's the first bond right here. And then the second bond is actually... I need to change the color. We'll change it to... That's a good color. The second bond is actually this right here. Believe it or not. I know that that's weird to think of. But again, remember, electrons are waves. They exist in both nodes at once. The bond is both parts of that. Now, don't accidentally put 4 electrons in there. I like to often represent it like this, like as a box, so I know that that's not 2 separate chunks, but that's just one bond. So I draw a little box like that. Whatever works for you. All right, we did a double bond. Let's do a triple bond, right? Oh, let's not. Let's have you do some examples here. These are difficult to draw out, but what I want you to do is, to the best of your ability, and I'm going to draw these for you when we get back here. Do this. Do the hybridized balloon structure, and label all of the bonds as either sigma or pi. I've given you some relatively simple molecules, and some of them have double bonds in them. We'll talk about triple bonds next, so give it a shot. I'm going to give you like... I don't know. I'm trying to burn time because I don't want to have tomorrow's lecture be nothing. So I'll give you like 6 or 7 minutes to do as many of these as you can. You'll probably be able to do the first 2. And honestly, that's good enough. I think the first 2 are the more complicated ones. So go ahead and do those. And paste your picture in the Discord for everybody to see, if you can do that. I have another little anecdote that the conversation in the chat just brought up. So in my Gen Chem class that I took as a student, so this is 2003 at UC Irvine, so almost 20 years ago. Holy shit. So I just made myself feel old, but I had to do this. So my instructor made us draw balloon diagrams, and we had to do it for the test, and so I drew mine. And my instructor liked mine so much, he wrote as a comment, "Surely you are a god of hybridized orbital diagrams." And I was like, "That's the nicest thing anyone has ever written for me." And it turned out that that instructor was a total douchebag. I later asked him for a letter of recommendation. He was super angry about it. So yeah. Drawing these gets you absolutely nowhere, it turns out. So don't feel bad if yours are no good. But I think it's a good exercise as long as you can recognize, like, oh, okay, I know where the orbitals are in space because that's what we care about. We care about the geometry here. That's the most important feature. All right, keep drawing. We'll see you in a bit. All right, we'll do 1 or 2 more minutes, and we'll go over the answers. All right, let's draw these balloon diagrams to the best of our ability here. Oops. Let's do this, because I'm going to have to shove this out of the way somewhere. So there we go. All right. I hope you enjoyed this diagram, because it's gone now. So we're going to draw CH2O. So if you aren't sure what orbitals to use, first draw the Lewis structure. So I'm going to draw CH2O over here. We're going to do that. So this is the correct Lewis structure for CH2O. And you can see that I have, on this carbon right here, I have 3 sigma bonds and a pi bond. So I'm going to need... that's not what I meant to write. I didn't mean to write sp2. I need this and 1 p orbital. So when I draw my carbon in the middle over here, I would have, in some direction, I'm going to go like this. And so there'd be my carbon. And so when I put its electrons in here, I would have... Well, let me draw its p orbital first, too. So this would be its p orbital going above and below the plane. And when I put my electrons in for carbon, that would be 1, 2, 3, 4. I'm going to put my oxygen over here. So here's oxygen. And my oxygen also needs to be hybridized, so we can form a p orbital and a bond. So here's going to be its sp2 orbitals. This is clearly not going to work. That's not the select tool. You know what we could do? We just do this. We don't need that diagram over there anymore. It's fine. And then oxygen will also have an unhybridized p orbital. But remember, oxygen looks like this, right? Three, four, five, six. This is what oxygen's orbitals look like. When I hybridize these for oxygen into sp2 and then a p orbital, which I should actually drop here. I'll just do that. So one of those electrons gets saved. That looks like this. So I'd have 1, 2, 3, 4, 5, 6. So there's my bond between carbon and oxygen, which is also down here. And then over here, oops, I don't want to replace this color. Here's a hydrogen, and here's a hydrogen. So it should look something like that. Let me see what you got. Oh, you didn't post it. Or you deleted it. I don't know. Just posted it in the Discord. I didn't see it. Am I in the wrong channel? No, I'm in the right channel. Yeah, I don't see it. Oh, there it is. I had to click on it to see. So it looks like your p orbitals are kind of invisible. You have the sp2 orbitals on the carbon and the oxygen. And you have the lines connecting where your p orbital should be. So draw in the p orbitals and then everything is correct. Like, I think it's fine. All right, let's go do the next one. CCl4 looks like this when I draw its Lewis structure. This one is just super obnoxious to draw, but it is really simple. For my carbon here, it's going to be sp3 because all I need are sigma bonds. Now, each of the chlorines is hybridized too because it is making a bond. So when I draw my chlorine atoms, I'm going to draw these as sp3 hybridized as well. And that's going to look like this. So if I draw out the chlorine orbitals, I have 3s and 3p. So that's what that's going to look like. I'm just going to blend everything together. And so I'll have 3 pairs of non-bonding electrons, and then this is the bonding electron. So let's draw carbon first. So here's carbon. It's tetrahedral. That was terrible. Try again. I can undo on my tablet. You can't really undo on paper. So it's, if you have a hard time with drawing it, that's totally okay. So there's my carbon. 1, 2, 3, 4. And then for my chlorines, each of my chlorines is going to look like this. So here's a orbital. And then it's going to have its own tetrahedral thing going on here too. So there's the paired, or the unpaired electron that we will pair. And then here's the other ones. And I basically do this 3 more times. And I'm purposely just trying to do this quickly with no regard to quality here. So that's the orbital I care about, but the rest of them, it's like whatever. And we could draw those out neater if we wanted to, but like really there's no need. We only really care about the orbitals that are overlapping. I should be labeling these with sigma and pi, so hold on. Let's go back up here and do that real quick. So we've got sigma, sigma, sigma. This right here is pi. And then these right here are non-bonding. And we could label the orbitals that are being used too. So we have an oxygen 2p and a carbon 2p. This is oxygen sp2, carbon sp2. And each of these is carbon sp2, hydrogen 1s. And then this is the same as this one up here. Down here, all of these bonds are the same. They are all sigma, carbon sp3, chlorine sp3. All right, let's do water. Water's real simple. Let's see here. There we go. So that's what water looks like. So there's 4 electron groups, so I'm going to have sp3. And my oxygen 1, 2, 3, 4, 5, 6. That's what its electron configuration looks like. I'm going to just blend it all together because I have 4 electron domains. And then there are my non-bonding pairs, which are these. And then there's my unpaired electrons, which I can use for bonding. So I'm going to draw my oxygen. And we'll draw an sp3 orbital, and an sp3 orbital, and an sp3 orbital, and an sp3 orbital. Ooh, I don't know why that one didn't draw. And then in 2 of those, I'm going to just go do. We'll put 1 electron in each of those. I don't know why I chose the upside down electron, but there you go. That's what it looked like for water. So we got our non-bonding. This is oxygen sp3, hydrogen 1s. That's a sigma bond. And this one's the same. All right, last one's oxygen, O2. I ran out of space. Well, we could probably cram it in here. There's what O2 looks like. This is kind of sketchy. Let me fix this. There you go. And so we can see that we have 3 electron groups around here. So this is going to be sp2, because I need to have a double bond in here, right? So let's do that. Oxygen, 1, 2, 3 electron groups. We'll make the p orbital go above and below here. And then I'll do the same thing with this other one over here. So there's my O. 1, 2, 3. And then this can go above and below. There we go. And then here's oxygen's electrons up here. Let's just assume that we saved one of these for a p orbital. So here's my electrons for this side. Pair, pair, unpaired. And then the other oxygen will do its electrons in purple. So 2, 4, unpaired, unpaired. 2, 4, unpaired, unpaired. Yep, all checks out. Here's a bond. We're using 2p orbitals from oxygen. This is a sigma bond in the middle. That's going to be our oxygen sp2 bond. And then non-bonding, non-bonding. There you go. All right, there's very little left to do in Chapter 5 that I care about. let me check to see how much there actually is left. So I have SP. We have SP. We have bond rotation. You know, let's do bond rotation real quick before we go, because that's like 2 slides. And since we've been talking about this, actually, you know what I'm going to do? Let's go back to this diagram here. I don't want to click on that yet. Okay. Looking at my O2 molecule here, I want you to try and imagine what would happen to this diagram as drawn if... I'm going to take a new color here. I'm going to take this... I'm going to try blue. We'll see how this works. I want to take along this axis with my oxygens that go through it. I want to try and torque this so that I twist it in this direction. So if I grab one end of the molecule and twist it, what will happen? So I'm going to grab the oxygen atom on the right, and I'm going to try and twist it like that. If I do that, this orbital is going to go back, and this one's going to come forward, right? What's going to happen to my overlap? Will these overlap anymore if I twist the right side of the molecule? And the answer is, well, no, they won't, because if this one goes to the back here, then this will be going up and down along this axis, and then this one might be going, like, say, that way. They won't be parallel to each other anymore, and so they won't line up. If you try and rotate around the central bond in this molecule, where it's a double bond, the pi bond breaks. And as a result, anything that has a double bond cannot be rotated around that axis. But if we go up here, and we look at this molecule right here, CCl4, if I try and do the same thing, that's terrible. Let me try that again. Along this axis, and I grab here and I say, let's spin this guy around. What happens? And the answer is, well, this part just spins around too, right? It will still overlap. The overlap remains. And as a result, we can rotate it. Because remember, all we care about for bonding is that the orbitals overlap, right? Sigma bonds go along the internuclear axis, so you could spin them all you want. And in fact, if I had other stuff bonded to this molecule over here going in this direction, this would all start twirling around like a top. And in fact, for molecules, they rotate stupid fast. Billions of revolutions per second. And if all we have are sigma bonds connecting everything, then everything just kind of spins independently, because all we care about is that the orbitals remain overlapped, so the electrons remain between the nuclei. It'll be stable that way. But down here for oxygen, if I try and torque one end and have the other one remain where it was, then I hit an issue. And the issue is that when I rotate this, these become unaligned. Because rotation breaks pi bonds. And so these ends will be fixed relative to each other. Double bonds, and also triple bonds, we haven't gotten to a triple bond, but that's okay, cannot be rotated. If you try and rotate them, the bond stays bonded, and the molecule just rotates the entirety of itself around with you. And so that leads to this sort of concept. So these two molecules, as shown, are identical, and it's because this bond can be rotated. And so what ends up happening is that this guy, which is up here but is down here, we can just swivel him to whatever position we want him to go to. And so I'm going to just turn him down to the bottom, and we have the same molecule, because this can just rotate however it wants. But then we come over here, and these two are stuck. I can't do this. Because if I do this, I end up flipping the entire molecule. So this other side would flip with it. So if I rotated it like this, I would end up with both my Cl's at the bottom. What I would not get is that. So in order for me to make the molecule on the left and the molecule on the right, I have to make those bonds before I make the double bond. So these molecules are unique. They are synthesized in different ways. So double bonds do not allow rotation. These are not equivalent molecules, and we actually give them two different names here. So you may have heard of these names, not in chemistry, but I mean, it is June, so it's LGBT Awareness Month and Pride and all those things. So we've heard of the term cis and trans. What cis means with regards to a molecule is that the functional groups that are distinct, so in this case it's chlorine because that's what we're using to name it, they're on the same side. Whereas trans means they're on different sides. And that's what those two terms mean. Just like how we describe someone as transgender, if their perceived gender does not match up with what they believe their gender to be, or that they prefer, I should say. Sorry, I don't know how to properly word that. So I apologize if that comes off as callous. But the intent is that this word, trans, is used in chemistry to represent this, because I believe that it's Latin. And so when we have our functional groups on different sides, we use the trans designation to indicate that. So when you get to organic chemistry, you're going to see cis and trans all the time relative to double bonds, specifically double bonds. And that's because the double bonds make these sp2 trigonal planar arrangements where this becomes possible. When we come back on Thursday, we're going to look at just sp bonding, and we're going to find that all those arrangements make linear. And linear is boring. Everything's in a line, so there's no interesting cis and trans chemistry that can come up. The molecule still can't rotate, but it doesn't really matter because it's linear. So it's going to be symmetrical anyway. So yeah, that's bond rotation. The takeaway from this is that single bonds you can rotate all day long, and so that molecules can be identical, even if they aren't drawn the same way on paper, because they rotate. But double bonds cannot be rotated, and thus these molecules are unique. All right. I've successfully used up all the time. Hooray. When we come back on Thursday, we're going to talk about sp hybridization, and then we're going to talk about things like sp3d and sp3d2. We can hybridize past sp3 if we use d orbitals, and because those are for elements that are breaking the octet rule, those have to be like third row elements like phosphorus or sulfur and so on. So we'll get to that on Thursday, and then we'll finish off the quarter. So there is no quiz for Chapter 5. That's going to all just appear on the exam. There are very basic questions on the exam about Chapter 5. We've covered most of them already. They'd be things like, can this rotate? Or how many sigma and pi bonds? Or what orbitals does this use? And so on. So there's no drawing of pictures, but I think it's important for your understanding. Thanks for coming out to the lecture. I think that that's all I have. There is a lab number 5, and that's going to be due around or after the final. Lab number 5 is basically a review of the first 4 labs. We give you wine and we say, hey, here you go, here's some data, figure it out. And like literally that's it. So the intent of that lab is use everything you've learned so far. Where's my music? There's my music. I need audio though. Hooray. Yeah, make sure you get quiz number 4 in tonight. It'll close tomorrow. I'll open that up for Thursday. Your exam's on Friday. Take care.